So let's plot this data first. So what I'm going to do here is I'm going to plot a displacement versus a time graph. So my time will go on the x-axis, so this is my average time taken from the average of these three trials. That will go into my time part of the table. I can also change this variable here. Usually it'll appear as x, but I can make it whatever I wish. So I'm going to make it a t to more closely relate to the data I'm collecting, and of course this is going to be an s representing the displacement. So here are my points, and I'm going to have a guess that because there's a slight curved nature in my points, I'm going to have a guess that this is going to be a quadratic fit. So I'm going to use my quadratic formula here, or quadratic equation formula, and I'm going to use a little tilde sign here instead of an equal sign, and that will plot a line of best fit for this data. So if I check on that now, you can see it's quite a good quadratic fit with an r-squared value of 0.9997, which is 99.97% accurate. Not much error in those points at all, so good job. Let me explain some of these values here and how they can be calculated, especially the ones absolute and percentage error. So here we have three measurements of time, 1, 2, 3. So this is based on the three trials that we took. We're plotting the average time against the displacement here, but this value here has got some error in it. Obviously you can see here the smallest measurement was 1.15 seconds and the largest was 1.33. So the absolute error is the difference between the average in this case and the smallest. Now it may be the average and the largest depending on which value gives you the greatest absolute error. You can see this is plus or minus delta, and in order to find the percentage you simply take your absolute error in your time, because this value is actually in seconds, and you add and subtract it to this average. So the percentage is 7.3%, which is 0.090 divided by 1.24 times 100. Okay, so that's the first thing you need to do before we move on to look at the velocity versus time graph. So let's now look at table 2, and this table will help us to plot the velocity versus time graph from the displacement versus time graph. Here are my displacement values, here are my time values. So these are the two columns that have been transferred from table 1. The other thing that's been transferred is my absolute and percentage error, because these are the errors, the percentage errors in the time that I measured. So to find the average velocity now, I just simply use velocity average equals displacement on time. I know my displacement and I know my time, so I can find my average velocity. Now to find the final velocity, because that's what I want to actually plot, I want to actually plot final velocity versus time. So to find my final velocity, I use this equation here. Final velocity equals 2 times velocity average. Now, where does that come from? Well, if we think about it, if we've got two intervals, the starting interval of time and the final interval of time. So we've got an initial velocity and we've got a final velocity. We add those two, so initial plus final, and divide by 2 to find the average. So that really is just an equation based on that. So V final equals 2 times velocity average. Simple, straightforward. There's my final velocity. So now I'm going to plot my velocity final graph versus my time. So here is my time column in Desmos T1, and my velocity column, the final velocity, is here. That's my final velocity. So just to show you what my end result will be, let's have a look at this sample and let's just investigate the differences in the 3 lines, because I've got 3 lines of best fit here. This blue line represents my final velocity versus my time. So if we go to the data table, we look at this point. Now this point has a final velocity of about 0.79 from the graph. If I go back to my table, here is that point here, 0.79. That's my final velocity at time 3.04 seconds. Now, each of these points represents the line of best fit that's represented by that blue dotted line. The red line represents the maximum line of best fit. That's when the absolute error for velocity is added to it, and the green line represents the minimum line of best fit, which means this velocity here has the absolute subtracted from it. So let's just have a look at that in a little more detail. So let's take this point here, which is 0.79. Now, according to my absolute uncertainty, I've got 0.05 meters per second uncertainty in this measurement here, because I measured time to work out velocity. So to find my maximum, I take that point and I add that point to it, which will give me 0.84. So let's have a look at that on our sample graph, and you can see up here there's that point, which is about 0.84, so correct. So that point there represents this point here with the added absolute uncertainty. If I take that average point and subtract 0.05 from it, I get 0.74. So let's have a look at it. There's my 0.79. I subtract 0.05 and I get 0.74, which is that point there. So that point belongs to my line of best fit for the maximum error, and this line of best fit for the minimum error. Now if I do the same thing, if I plot each of these points where I take into account the absolute errors, I should get 2 lines. The red line, which represents my maximum line of best fit, and my green line, which is the minimum line of best fit. Let's now do that in Desmos. Now the first thing I've done is I've come across here and I've created a column in Desmos. A column, here it is, I'm calling it A for absolute error, and I've put all those values into that column. Okay. Now if I go back to my graph, so here's my blank graph, and here are my values from the table for the final velocity. Now I can draw a line of best fit for this line. V1 tilde equals MT1 plus C. That is acknowledging that it's a straight line of best fit. So if I check that, there is my average line of best fit for the final velocity versus the time. Now what I'm going to do is I'm going to come here and I'm going to draw the graph for this data here, which is my minimum line of best fit. So I'm calling M1 the line, the minimum line of best fit. So you can see here I've got M1 tilde MT1 plus C. That means it'll draw me a line of best fit with a gradient M for this set of data. So if I check that, there I've got the points, and then if I check that, try again, there I've got my minimum line of best fit. Do the same for M2. M2 represents my points where I've added the absolute value, so I've gone 0.32 plus 0.02 to give me 0.34, and they're my points for my maximum line of best fit. There's my regression equation or formula. If I check on that, as you can see now, I have three lines. The green one represents the final velocity, the average of the final velocity versus time. The red one represents the maximum line of best fit, and the blue one represents the minimum line of best fit. So now I have plotted my graphs to reflect my errors. I want to show you how to add these vertical error bars using Desmos. Now, these can also be drawn in Excel, but I think Desmos provides a more user-friendly environment than Excel, but look, it's up to you. So let me explain how to do it in Desmos. What I'm going to do is I'm going to create an equation that represents my absolute errors in the y components, or the y-axis, which represents my final velocity. So I'm going to take the values in my domain, my x. So I'm going to type in here an x, which means it'll take the values, my x values for these points, and it will build the vertical lines for my time and my velocity. So time being my x value and velocity being my y value. So here I've got T1, so it's going to take the T1 values, and I'm going to use this type of bracket. Then V1, so V1, it takes this value here, and from it subtracts this value here to give me my minimum value that fits on the minimum line of best fit. And this is my lower limit, and this is my upper limit. So this is saying, well, I'm going to take V1 and I'm going to add 0.02 to it to give me 0.34. So that's how you would write your formula, if you like, in order to get these vertical line bars plotted. After you do it a few times, hopefully you'll get used to it. But what I'm saying is, this is the x values, the domain, the x values. This is my y values, and these are my values that have the absolute error either subtracted from them or added to them. And then once you check this, there are my error bars, my vertical error bars, and it gives you an idea of the two lines and how they're actually plotted with the line of best fit. Okay, so hopefully that gives you something to work with. So all the experiments you'll do from here on in, this is how you'll perform the error analysis. Good luck.